Okay, now here you have oscillations. So before we start vibrations, I have explained earlier. Okay, before we start vibration, okay, we have to look into the oscillation. So what is oscillation? So here in the next page here, we have oscillation is actually defined as a to and fro motion. A to and fro motion. So when you look into the diagram, okay, so we have a mean position here, or we can sometimes call this as the equilibrium position. So as you look at the mean position or equilibrium position, I have a particle, a red particle here, which is moving from point O to point A, then from A to B, B to C, and C to D, back to the mean position, but it is only half an oscillation. Then it moves to E, then to F, G, and back to O. So once it has completed, okay, its movement towards left and to the right, back to the mean position, we consider that as an oscillation, one oscillation. Okay, so oscillation is actually defined as a to and fro motion about the mean position of the particle, and is completed when the motion moves, when the particles move from O, okay, to B, and then to F, back to O. That is an oscillation. Hello? Now an example of oscillation here, we have the pendulum, okay, the pendulum mechanism. So when you look at the pendulum here, we have a bob, this we call a bob or a ball, okay, a bob, and a rod here which is attached to point O. So when you let it go, it will start to swing, okay, about the center line here, which is known as the mean position, about its mean position. So the bob, as you can see, the red ball or the bob here is oscillating towards the left and then back to mean position, towards the right and back to mean position. This is considered as an oscillatory motion. Okay, so this is one example. And the second example that I have here is a spring mass system. Spring mass system. So you have a spring which is attached to a mass. So when you let it go, at the first diagram, when you let the mass drop vertically downwards, what happens is the spring will start to oscillate. So when the spring oscillates, when the spring moves vertically downwards, what happens is the spring is extended. So when the spring is extended or elongated, it will tend to restore back to its original position. That means about the mean equilibrium position. So what happens is the mass and the spring will start oscillating about its mean position. So this is another example of an oscillatory motion where the spring and the mass are placed vertically. You know, sometimes you can consider horizontal spring mass, okay, but then you have to consider a frictionless surface, for natural oscillation or natural vibration. So now the next term that we have to define is the periodic time. So what is periodic time? That is the time required to complete one oscillation of motion of the particle. So you know what is an oscillation already, right? So one oscillation actually is equivalent to one cycle or one revolution, that is 2 pi radians. So the time to complete 2 pi radians, or the time to complete one oscillation, is called the periodic time, or in short we call it as the period. So based on the periodic time, we have another term which we call frequency. Frequency is actually defined as 1 over periodic time, that is 1 over second. And we have to know that 1 over second is actually equals to 1 hertz. 1 hertz. So the time required to complete one cycle or one revolution or one oscillation of a motion. the number of cycles made per unit time, is known as frequency. So if you take 1 over periodic time, you get what we call frequency. So frequency is defined as 1 over periodic time, and it is measured in hertz. So that is equivalent to 1 over second, 1 cycle per second, or 1 oscillation per second, or 1 revolutions per second. Clear? Then the next term that we have to define is what we call displacement. A displacement and amplitude. So first thing is we have to know that displacement is denoted by a symbol of x. Okay, we use a symbol of x for displacement, and displacement is usually the distance measured away from the mean position, of an oscillatory particle. Okay, so the displacement is measured away from mean position, either to the left or to the right. Okay, from the mean position. That is called the displacement. And for amplitude, we can use a symbol of A or R. A stands for amplitude, or R the radius, amplitude. Okay, so amplitude is actually the maximum displacement. Okay, it's defined as the maximum displacement of an oscillatory motion. Okay, so the maximum displacement on either side of the mean position is known as the amplitude, the maximum displacement, and this is how you measure it. So from O, the horizontal distance from O to the point B, or to the point B where your red particles reach just now. Okay, so O to B, the horizontal distance from O to B is called the amplitude. If O to A, we can't call it as the amplitude. We can only call it as the displacement of the oscillatory particles. Okay, so you can consider the horizontal distance from O to B. Okay, that is the amplitude, or O to F as the amplitude, the horizontal distance. So O to A, or D to C, or D to E, or O to G, those are known as displacement, because it is not the maximum displacement yet. Follow? So the next one. So that is how you measure displacement, and that is how you measure the amplitude. Okay, the X stands for displacement, the R stands for the amplitude, or the maximum displacement. So here, okay, I have a diagram that showing us that the red particles, okay, while the red particles is moving in a cycle, okay, the blue particle, okay, that reflects the red particles will be oscillating about the center line of the circle, that is the mean position. So from here, you can see, okay, so the red particles actually is moving in a cycle, moving in a circular path, and while the blue particles will be oscillating horizontally about the axis, or in the radial position of the circle. So, and that reflects, okay, the motion of the red particle, which is moving in a circular path as well. So simple harmonic motion. Okay, what is simple harmonic motion? There are 2 points, there are 2 important points that we have to refer in order to define simple harmonic motion. Okay, the most common form of oscillatory motion is known as the simple harmonic motion. So an oscillating body will have SHM, that is the simple harmonic motion, if at any instant during the cycle there are 2 points that it has to fulfill. One, the acceleration of the body the acceleration of the body is proportional to its displacement from the mean position. So the acceleration will be maximum when the displacement is maximum. The acceleration will be zero when the displacement is zero. That is what it is based on the first point here. So they say that acceleration of the body is proportional to its displacement from the mean position. Means that when the displacement increases, the acceleration will increase. When the displacement decreases, the acceleration also will decrease. Okay. Then the next is the acceleration of the body is always the acceleration of the body. You see on both the velocity triangles here or polygons here. You can see on one of the diagram you can see there are blue arrows that is moving towards, or a red arrow that is moving towards the mean position. The mean position of the oscillatory particles, the red particle. Okay, so the second point, in order to fulfill that the simple harmonic motion, okay, the second point is the acceleration of the body must always be directed towards the mean position, or equilibrium position. So those are the 2 points that you have to refer. So here you can see the diagram. In the diagram, you can see the red particle is moving from P to P prime. So when it is moving from P to P prime, it has been displaced by an angle of theta. Okay, and we know from the basic dynamics equation that the angular displacement theta is actually equals to the angular velocity omega multiplied by the time. Okay, the theta, the angular displacement, is actually equals to omega t, where omega represents the angular velocity and the t represents the time. Follow? Okay, so based on this, from the diagram also you can see the x which represents the displacement of the particle. Okay, and then from point O, that means from the center point of the circle, I didn't show the O here, from the center point of the circle to point A, or from the center point of the circle to point B, is actually considered as the amplitude, the maximum displacement. So that is why sometimes we say amplitude can also be equals to the radius. Okay, so because radius is actually based on this diagram is the maximum displacement. That's the amplitude. Okay, and then so based on the diagram that you have here from OQP prime, the triangle having an angle theta and having a displacement of x, and then from O to P prime or O to A is actually referring to the radius of the circle or the radius of the circular path of the moving particle, red particle. So that is the radius and the displacement. So to find the opposite side of the triangle, okay, you can take opposite to hypotenuse, okay, that is sine omega t or sine theta is equals to the P prime Q side, the opposite side, divided by the hypotenuse, that is the radius. Or you can consider also that P prime Q, okay, if you want to find by taking opposite and adjacent, okay, that is tangent. Okay, it's up to you. So the next part here shows, okay, I have 4 different circles here, 4 different diagrams here, showing that the the red particle is actually moving along the circular path, and where the blue particle is moving in a horizontal straight line, oscillating about the horizontal straight line. So in order to determine or to see at which position that the velocity is maximum and at which position that the acceleration is maximum and at which position the acceleration is minimum. So from these 4 diagrams, you will be able to determine the Vmax, the Vmin, the Amax, the maximum acceleration and the minimum acceleration. So based on the diagram, the first circle here, okay, we have displacement q, that means the q here, the displacement is x. So x, you can find x by taking r cos theta. R is what? R is the radius from O to P prime. From O to P prime, that is the radius. So the angle theta here, okay, is the angular displacement, which is equal to omega t, and you have the displacement x from point O to point Q. So from here we can define that the displacement of Q, okay, is actually equal to r cos theta. And we know that the angular displacement theta is actually equals to omega t. Can you see that? So you have the formula for displacement for the oscillatory motion of the red particle equals to x equals to r cos theta or r cos omega t. So the horizontal component of the tangential velocity p relative to O is the velocity of q towards O. Okay, is the velocity of q towards O. To find the velocity based on this equation, x equals to r cos omega t, what we can do is we can differentiate the x with respect to time. Okay, velocity to be dx over dt, or you can denote velocity as x dot equals to dx over dt. So you differentiate this equation, which is x equals to r cos omega t with respect to time, you will have v is equals to negative omega r sine theta or negative omega r sine omega t. That is the velocity of the red particles. So that also represents that the velocity of the blue particles moving from point A towards the mean position or towards point O. So that is given as negative omega r sine omega t or sine theta. So the minus sign actually indicates the velocity is increasing while the displacement is decreasing. So velocity will increase when displacement decrease. For example, if the red particle is at point A, what is the angle? The angle should be theta, correct? When the red particle is at point A, so the angle theta is equals to 0. So when you look into this, okay, which we have v equals to omega r sine theta, and when theta is equals to 0, sine 0 is 0. Okay, so 0 times omega r, you have 0. So the velocity would be 0 at when the red particle is at point A. Follow? Okay, so at maximum displacement, when the x is maximum, what is the velocity at point A? So the velocity is 0. So that indicates that the velocity increase or decrease, increasing when the displacement decrease. The velocity will decrease when the displacement increase. Okay, that is the negative sign. Notice that as q moves from O to B, from O to B, from O towards B, the velocity is decreasing and the displacement is increasing. So when the blue particles move from point O to point B, so when it reaches point B, that is 180 degree. If you were to measure, it will be 180 degree. Sine 180 degree is how much? Is 0. So the V is 0, but the displacement is maximum, which is equals to its amplitude. That is based on the circle itself. So as you can see, okay, from both the diagram, okay, I have, okay, the first diagram, A, from point A, the blue particle is moving towards from point A back towards the left, back to point Q, and then to point O, and then to Q prime on the next diagram. Okay. So while the red particle is moving in its circular path, the blue particle is actually oscillating along the horizontal plane. So the other two diagrams here, okay, So based on these two diagrams, okay, so you can see that when the red particle is moving, the first one moves up to, let's say that is 207, roughly around, how much is that? Alright, 80, 60, that means it's 240. Roughly at 240, the blue particles will be moving from point Q towards point B already. Then the last diagram, it shows that the blue particle is actually going to the mean position and then going back towards the right, back to point A. So that is an oscillation that is considered as a complete oscillation. So the horizontal of the centripetal acceleration of P towards O, the acceleration of P towards O. That means when the particle moves from point P towards point O, the acceleration of the particle is considered as a centripetal acceleration. Okay, centripetal acceleration. That is equal and opposite to the centrifugal acceleration. So how to obtain the formula of A equals to negative omega square r cos theta? That is by differentiating the velocity with respect to time one more, or differentiating the x or the displacement with respect to time one more time, that means twice, or differentiating the velocity with respect to time. You will get acceleration which is equals to omega square, negative omega square r cos theta or cos omega t. So now you can check when theta is equals to 0, that means at point A, you can check. At point A, when the angle is 0, because the red particle is moving from A, okay, then towards P prime or in the anti-clockwise direction, right? So when A moves in the anti-clockwise direction, at point A itself, at point A itself, angle theta is actually equals to 0. So when the angle theta is 0, cos 0 gives you 1. Cos of 0 gives you 1. So omega square r. So the acceleration will be equals to omega square r. That is the centripetal acceleration, r omega square. The centripetal acceleration. So when the theta is 0, then the A is maximum, correct? When theta is 0, A is maximum. When theta is 0 is when the x is also maximum. When the x is also maximum, that is the amplitude. So at maximum displacement, you have maximum acceleration. So that proven the first point of SHM. The first point to fulfill for the simple harmonic motion is proven that when amplitude is maximum, acceleration is also maximum, which is the centripetal acceleration, and it is equals to r square omega. Okay, sorry, omega square r omega square. And the minus sign also indicates that the acceleration is always opposite directions to the displacement. Displacement is measured away from mean position. Acceleration is always towards the mean position. Okay? So from this part, I'm actually defining or proving out the formulas for both the periodic time and the frequency. So we can also call that the omega, which is equals to the square root of acceleration over displacement, is actually known as the circular frequency. Circular frequency, which is in radians per second. And t, that is periodic time. And the lowercase letter f is known as the frequency. So based on displacement, x equals to r cos omega t, you differentiate with respect to time once, you get negative r omega sine omega t or theta. And we got to know that, okay, the r omega sine theta can actually be equals to omega square root of r square minus x square as well. Okay, that can be proven out. Now then the acceleration A, what you have to do is differentiate the velocity with respect to time once more. So you get r omega square cos omega t, where omega t is equals to theta. Okay, so you have r cos theta is actually equals to x. So that is why you have omega square x. x is the displacement, omega is the circular frequency. So based on that, you can manipulate that and you get circular frequency equals to square root of acceleration over displacement. And since that circular frequency is equals to 2 pi over periodic time t, so you can write out that t, the periodic time, is actually equals to 2 pi to the square 2 pi square of displacement over acceleration, or simply the frequency you can just take as 1 over periodic time. Okay, and then the next one, it shows you that the frequency is equals to 1 over 2 pi square of angular accelerations over angular displacement. How from acceleration over displacement can be changed to angular acceleration over angular displacement? So you have to refer to the formula that I've given above here, that is from your basic dynamics that you should have studied quite some time ago, okay, before you come to this course. So you have converted the linear to angular form. Okay, so that is the frequency while the object is rotating. So the last part here is to show you the differential equation of simple harmonic motion. Okay, so the standard differential equation of simple harmonic motion is actually given by x displacement equals to a cos theta omega t plus b sine omega t, where a and b, they are the constants. Okay, so based on time 0, displacement is actually equals to the amplitude radius r, right? Okay, when theta is 0 or when time is 0 at point A, okay, theta is 0, the x, the displacement, is actually equals to the amplitude. Okay, so you have this, okay, where when t is equals to 0, x is actually equals to the amplitude, the radius of the circular path. When point P and Q lies at x, lies on x, A should be equals to R. Okay, A should be equals to R. Because when you refer to the equation, okay, cos theta, when theta is 0, cos 0 is 1. Okay, cos 0 is 1, which is equals to A, and B sine omega t sine theta, when theta is 0, sine 0 becomes 0. 0 times B, you have 0. So x is actually equals to A. This case, x is equals to A. So that is why we say x equals to A, and where A is actually the amplitude. So when you refer back to the earlier diagram, you can say at point A from a mean position is actually the amplitude. Okay, so you have this. So differentiating that, you have V equals to omega r sine omega t or theta. For acceleration, you differentiate one small time with respect to time. And then you substitute, okay, your theta, which is equals to 0, or when your theta is equals to 180 degree, okay, or when theta is 90 degree, and you see what is going to happen with the equations that is given. And finally, you will come across, okay, d square x over dt square plus omega square x equals to 0. That is the differential form or the differential equation for simple harmonic motion. That is in the differential form. Okay, so that is the equation that is commonly used, where d square x over dt square is actually referring to the acceleration. Omega square x, okay, or the x here is actually referring to the displacement. Okay, so that's all for this section. So here are some examples for you to try out, and the solutions will be given later on. Okay, the solutions will be given later on. So that's all for today.